Hello everyone, welcome to this lecture 43 in the NPTEL course on Riemannian geometry. So as I mentioned at the end of the previous lecture, for the next few lectures we are going to analyze when, if you are given a geodesic, when is it actually a minimal geodesic, right. And the motivation or the inspiration comes from this humble sort of second derivative test from multivariable calculus. So let me remind you of what the second derivative test is. So remember, suppose you have a smooth function, actually C2 function is good enough, but let us just assume we have a smooth function. So let us say this is smooth and let us say a point P in the interior is a critical point. Okay, so let h of P be the Hessian of the function at P. Okay, so this is del squared f by del xi del xj at P, where I and j range from 1 to n. Then by Clairaut's theorem, h of P is a symmetric matrix. So the second derivative test says the following: that if P is a local minima, then this implies that this symmetric matrix is non-negative definite. Okay. So in other words, it is a symmetric matrix, so it will have n real eigenvalues, all eigenvalues are non-negative, or equivalently for all vectors v in Rn, but you should think of this Rn as the tangent space to omega at this critical point P. Non-negative definite just means that if you take this Hessian applied to V, so that is a matrix, so you can apply it to V, take the inner product with V itself, this is non-negative for all vectors V. Okay. This is equivalent to the statement that all the eigenvalues are non-negative definite. So now how do you actually calculate, I mean how do you calculate this inner product, right, because that is the thing that we would want to generalize to our situation. So let gamma, capital gamma, be a path, be a curve in omega such that let us say gamma of 0 is this critical point and the derivative at the critical point is precisely this vector V. Okay. So then a simple calculation shows the following, it's basically using chain rule twice, that this is simply d squared by ds squared at s equals 0 of f composed with gamma of s, right. So the idea is that you have your P, you have your vector, you take a curve gamma passing through P with that as the initial velocity vector, and you restrict your function to this curve gamma and compute its second derivative, then that is precisely this. Okay. And so then by the second derivative test in one variable calculus, this would be non-negative if P is a local minima. Okay. So in fact that is how one reduces the sort of second derivative test in higher dimensions to the second derivative test in single variable calculus. Okay. So the idea for us will be to try to compute a quantity that looks like this. So for us, what is going to be the dictionary? So we will replace omega by the set of admissible paths from two given points P and Q. this F is actually going to be the energy functional, this point P is going to actually be a geodesic, okay, and this capital gamma is going to be a path in the space of admissible paths. So in other words, it is just going to be a one parameter variation, admissible variation, okay, and then I would like to mimic this second derivative test, okay. So that brings us to the key point of this lecture, namely the second variation formula, okay. So here's the theorem. Before I state the theorem, let me maybe introduce some notation, or actually let me remind you of some notation. So let gamma be an admissible variation, right. Then I want to set, as before, little gamma s of t is just gamma s comma t, okay. So remember gamma was defined on something like this, and then I am going to denote by capital S the sort of transverse derivatives of gamma, and by capital T the horizontal derivatives of gamma. So these are basically just the velocity vectors of these curves gamma s of t, okay. So that is going to be my notation, capital S and capital T, okay. So the statement of the second variation formula is the following. So let little gamma be a geodesic. So like in multivariable calculus, it makes sense to talk about the second derivative test only at critical points. So we start off with a critical point, so of the energy functional, which is a geodesic. So let gamma be a geodesic and capital gamma an admissible variation. An admissible proper variation. Okay, what is the meaning of proper variation? That just means that gamma s at A is P, gamma s at B is Q for all s, okay. Otherwise this capital gamma will not be a path in the path space omega of P comma Q, right. And suppose the variation vector field is W. So W is basically this S evaluated at 0 comma t, okay. Then the second variation formula says the following. So if you take the energy functional on these curves gamma s, if you compute the second derivative and plug in s equals 0, then that is given by this formula. Okay, minus you will have now a curvature term. Okay, and of course capital W need not be smooth. So by definition what this really means is that you actually take the integrals over the smooth parts and then sum them over. Okay, where as usual we have this partition and gamma restricted to this closed interval is smooth. Okay. So let me make a quick remark which will be again useful in the proof. So for all t in this interval, this is actually smooth in S as a, so if you fix a time t and let S vary between minus epsilon to epsilon, this is actually smooth. Okay. So this will remember, even in the first variation formula this was used, but it will also be useful in the second variation formula. Okay, so let us try to prove this. So by the calculations in the first, so of course if you want to compute the second derivative, you first have to compute the first derivative, but luckily for us we have already calculated the first derivative. So by in the proof of our first variation formula, so by calculations in the proof of first variation, right, if you take the first derivative, that is going to be the integral from a to b of this. Okay. Okay, so now we differentiate once more. Okay, so d squared by ds squared of epsilon gamma s. So by the fact that we are dealing with metric connections, this is going to be, so maybe let me write like this. So d by ds, okay, which is going to be the integral from a to b of ds dt of s comma t, plus there will be another term which is basically dt of s comma ds of t. Okay. Now let us analyze the second term. Okay, so the second term has an integrand that looks like this. So firstly, I mean it has a term that looks like this, but what is this? Sorry, let me look at the other term, right. So if you look at this term, right, what is that? That is basically ds del t of gamma, but by the symmetry lemma that was also proved that also proved useful in the proof of the first variation formula. This is the same as dt del s gamma, which is the same as dts. Okay. So the second term is precisely the integral a to b of norm dts squared. Okay. All right. So now let us look at the first term, that is where the curvature will come in. So the first term, the integrand is so the integrand is given by ds dt of s. So ds dt of s, but then if you note that the commutator, so if you take minus dt ds of s, so that is just the commutator, then that is precisely equal to the curvature term. So it's precisely equal to S comma T acting on S. Why? Because clearly del by del S and del by del T commute. Okay, so they are like independent variables, so they commute. Okay, so then this commutator will precisely be a curvature term. So that means that the first term, which is basically the integral from a to b of ds dt s times t, is going to be precisely the integral from a to b of dt ds s comma t plus some curvature term. Okay. So for the first part, I now pull out, this is the standard trick, I pull out this dt out common, right. So I write this as d by dt of ds st. So if you compute d by dt of this, you will first get exactly this term, but then there will be another term which I now need to subtract off. So minus the integral from a to b of ds s dt t, okay, and then the curvature term which is Rm of s t s t. Now in the curvature term, because I want to in applications I want to make it look more like a sectional curvature term, I swap these two. Okay, so the curvature, so the result will be the following. Okay. Okay, so let me now plug in t equals 0. So let me s equals 0. So now let me plug in okay. So what is the first term at s equals 0? Okay, so let us go back a slide. So at s equals 0, if you look at this term, what will be this? This will basically be dt of gamma dot. So at s equals 0, I will have the following, sorry. So the integral from a to b d by dt of at s equals 0, then you will have another term that looks like sort of ds s at s equals 0, but then the other term is dt capital T at s equals 0. So that is precisely just dt of gamma dot, okay, and then you have the curvature term. W comma gamma dot w, okay. But then this is 0 because gamma is a geodesic, okay. and I will call the first term as delta. So I am going to call this as delta, this entire thing, okay. So this is going to be delta minus the curvature term, okay. Similarly, if you take the second term, so the second term at s equals 0. So let's go back to where we computed the second term. So the second term was basically just this, but if you plug in little s equals 0, then this capital S at little s equals 0 is just the variation vector field W. So the second term is just going to be the integral from a to b of the covariant derivative of W, okay. So we get the following formula for the second variation of the energy. It is delta plus the integral from a to b of this squared minus the curvature term, okay. So to finish off the proof, I need to have the following claim, that this delta term is actually 0, okay. So then I would have proved the second variation formula. So why is that the case? Okay, so this takes up a little bit of space, so let us go to the next slide. So let me again rewrite that delta is 0 and let us prove. So what was I mean by definition, what was delta? It was basically d by dt of dss times t, okay, times in fact gamma dot, and you plug in s equals 0, right. You are integrating the time interval. So by the fundamental theorem of calculus, this is basically going to be the summation from k going from 1 to m, right. So maybe let me write an additional step, because my variation may in general be non-smooth. So this is precisely this, right. So on each of these sub intervals I apply the fundamental theorem of calculus. So this is going to be summation k going from 1 to m of ak minus comma gamma dot at ak, okay. Minus okay. So now we will have basically these two boundary terms when k is equal to 1, because when k is equal to 1 ak minus 1 will be just a, and when k is equal to m ak will just be b, right. So we will have these two boundary terms dss at b minus times gamma dot at b minus minus something coming from the left boundary, and then all the intermediate terms, right. So this will just be summation k going from 1 to m minus 1 now, right, comma so let me just make sure that I have got the sign correct. So when, for instance, when k is equal to m minus 1, when k is equal to m minus when k is equal to m minus 1, so am minus 1 plus will show up with a positive sign. So this should be there should be a minus sign here. Yeah. So you can carefully check that this is indeed the case. But now notice that at t equals ak plus at t equals ak, S is actually a smooth vector field in the variable little s, right, which means that this is the same as this, okay. So which means that these terms are 0, this summation k from 1 to m minus 1, this entire thing is 0. On the other hand, capital gamma is a proper variation and hence even the boundary terms are 0. So the boundary terms are 0. Okay. So that basically proves that that delta is 0, and that completes the proof of the second variation formula. Okay, so now the final thing I want to do in this lecture is to actually apply the second variation formula to get some sort of a second derivative test. So for that it is useful to introduce the following definition of namely the index form. So let gamma as above be a geodesic, okay. Then here is a definition. So the index form, it's useful to so a priori in applications you want to restrict the index form to essentially variation vector fields that come from proper variations, but for later applications it is actually useful to give a slightly more general definition of the index form. So I will define the index form to be a symmetric bilinear form on the space of all admissible vector fields, okay. Okay, so this is just going to be the integral from a to b of w1 prime of the inner product of the covariant derivatives minus a curvature term, okay. So in particular, suppose W is in the tangent space to omega pq at gamma. So what do I mean by the tangent space to omega pq at gamma? These are precisely the set of admissible vector fields along gamma which vanish at the two endpoints. So here p is equal to gamma of a and q is equal to gamma of p, okay. So then if gamma of st is a variation vector field, so if gamma of st is a admissible variation with w as the variation vector field, so that how do you construct these variation vector fields? For instance, you can just take gamma of st to be the exponential at gamma of t of s times w of t, okay. So then if you take the derivative of this at s equals 0, then that is precisely going to be w of t, okay. So, if you take such a vector field, then the second derivative of the energy functional at s equals 0 by our second variation formula is precisely the index of W applied to W. Okay. So, in other words, the index form, if you restrict it to the tangent space of omega pq, is basically the bilinear form associated to the second derivative of the energy functional. Okay. So, note that I gamma is a symmetric bilinear form. Okay. So, then the key sort of second derivative test is the following proposition, that let gamma be minimal Okay, so then I gamma restricted to this tangent space is non-negative definite. Okay. So that is for all W admissible vector fields which vanish at the end points, the index form is non-negative definite. Okay, so let me quickly give a proof and then I can stop. So let capital gamma S T be as above, such that W of t is its variation vector field. Okay, so then by Cauchy-Schwarz, okay, so by Cauchy-Schwarz I have the following inequality, that if you take the energy of these gamma s's, then that is bigger than or equal to 1 by 2 times b minus a times the length of gamma s squared. But now we are assuming that gamma is a minimal geodesic, so this will be bigger than or equal to the length squared of gamma itself, right. But then because gamma has constant speed, it's a geodesic, right. Because it has a constant speed, you can check that you will actually get equality in Cauchy-Schwarz. So this is precisely the energy of gamma. In other words, gamma is a local min for the energy, okay, at least along this one parameter variation capital gamma. So then by the first derivative test in by the second derivative test in one variable calculus, if you take the derivative squared of the energy functional, that is going to be non-negative, but then we saw that this is precisely the index form. Okay. So the index form is non-negative definite, and here W was an arbitrary vector field in the tangent space to omega pq. So this completes the proof. Okay. All right. So in the next lecture I am going to analyze, in the next few lectures I am going to sort of analyze this index form a little bit more, and we are going to refine this second derivative test, again all the while taking inspiration from multivariable calculus. Okay. All right, so that is it for this lecture. Thanks for your attention, and I will see you in the next lecture. Thank you.